Good afternoon, everyone present physically here in Tunica or remotely. We agreed to convene again at 3:30, and when I last spoke to you, we were going to have Narges talking, but unfortunately, I've had to persuade her to delay again because the other speaker has to get a plane back to Paris and would be at risk if he were to keep his other slot. So, with both of their agreements, it's now my pleasure to invite Jean-Marc Denis to speak to us. Jean-Marc is the Chief Strategy Officer of CyPearl. I like to say CPearl because it sounds more French.
You won't.
But you will tell us how to pronounce it. And this is this interesting new company that's in place to manufacture the European processor. And you're going to tell us a few things which are interesting, I think, about that and how it presents real opportunities for co-design as we move into this exascale era. So you've got 25 minutes. You have 20 minutes, and then there'll be plenty of discussion, I anticipate. So I'll let you know when you have 5 minutes to go.
Okay, so thank you all. Thank you, Peter, for the introduction. So about how to pronounce. CPearl stands for silicon pearl, from the black pearl, Arabian pirate, pirate. So it really consumes. There is an anecdote about it. So the French people used to say CyPearl because it looks very British and in the US. And in UK and in the US, they say CPearl because it looks very French. So the way you want. Honestly, as long as you remember the name, it's fine. So CPearl is a company, as you have explained, that design and manufacture. We are a fabless company, and we don't have a fab. A CPU, a general purpose processor, that is 100% developed in Europe. This is totally new HPC segment. We start with HPC segment, which is a big challenge. It's like climbing on the top of Everest. If you have never visited the Alps before, something like that. So it's very, very challenging. So I guess that most of you don't know the company and what we do, who we are. So let me make a very short introduction, very, very short. So it's a company that we have created. I'm one of the founder of the company in June 29. And it's coming from the European Processor Initiative that I initiated when I was at Ethos, which was before Bull. I'm the one who created the HPC business at Bull back in 2004. It's not from yesterday. So the CEO is Philippe Noton. He's a driver in the car, and my role in the company is to be the GPS in the car. So Philippe relies a lot on me, only for finding the right direction for the future. So today we have 4 design centers in France, 2 around Paris. Not in Paris, it's inside the city because it's far too expensive. But on the west and south of Paris, 1 in the region of Nice, Sophia Antipolis, and 1 in Grenoble. In France, this is the hotspot for the semiconductor industry. We have 1 design center in Duisburg, Germany, close to Düsseldorf, and 1 in Spain at Barcelona, because it's one of the technopole in Spain. And we anticipate to open new design centers, all R&D centers in Europe, and eventually also UK, which is part of Europe in many aspects, this year, or the year, or the next year. We have veterans of the semiconductor and HPC industry, like those STMicro, Marble, Local, well, you can see. So what we design is processors, no accelerators. We have absolutely no ambition to design accelerators, just make CPUs based on ARM instruction set for the first generations. Very specifically, it is based on the ARM Neoverse V1 core, which is by chance for us the core that is the AWS Graviton3 processor. So when you work on AWS Graviton3 based instance, work on the same core as my CPU. It's not the same processor. There are many differences, but at least the core is identical. So today we are 110 people, and we have new people onboarding almost every day. From week to week, we have 4 to 6 more people coming aboard. So our ambition is to be about 200 people by the end of the year. If we are lucky and if we execute well, 1,000 people by 2025. As I mentioned, we have locations, European places. One remark about our resources, I mean compute resources. They are all located in Europe, all located in France, in the region of France, the capital city for Champagne region, because we don't want to go to cloud operators, French, European, or US. We want to control our data. So we don't go and we will never go to cloud operators. For us, it's very constraining, that's the real cost, but at least we have full control about what we are doing. And it's crucial for having a complete security. Ah, yes.
Oh, it's for both of them. Oh, I see.
Is it-
Okay.
Is it
Thank you.
better now for the people who are remote?
Yes.
Yeah, okay.
Sorry.
Sorry, I didn't know. So this year, next year, we will expand around Europe. We will also have very likely a subsidiary in Taiwan because we manufacture at TSMC. So we must, and it's a must have, we must have a location with people in Taiwan to interact and to interface with TSMC. The process we are going to use is 6 nanometers for our processor. So our vision and strategy for the years to come is quite simple. We start with HPC, with CPUs for high-end supercomputers. So what we target is the top of the top 500. Then we will downscale the technology to data center and cloud computing. So there are many actions going on with cloud operators and server designers for data center. And then through time, not before 27, we will also start addressing the infrastructure edge segment because the volume and the demand is just massive. So we are going to move from the most demanding technology with very limited volume of production to massive volume production on the less demanding technology segment, but very competitive. So this is the only way for us in order we can sustain our growth on the reinvestment on R&D. So in terms of overall roadmap on the articulation of the product we are designing with the European, with the Euro HPC strategy. So I will not elaborate on Euro HPC. You know, we have discussed about it earlier this morning or maybe later today and tomorrow. So the ambition is to be with our processor in the 2 first exascale machine that will be installed in Europe, the one in Germany. So it's been announced that Jülich will host the first exascale machine in Europe. The second one will very likely be installed in France. So the RFP for the hosting entity will start in H2 this year, so maybe in September, October. So we should be in the 2 machines with the first generation of processor in the first machine, the second generation in the second machine. And what is very interesting is that we start working with ARM because it's a mature software ecosystem. It's a mature instruction set with almost all applications already ported on ARM. So with very high TRL, technical readiness level. And in parallel, we start developing RISC-V based technologies at the IP level in order we can mature the IP and the software ecosystem to be ready with high-end solutions by the end of the decade. So we don't believe that with RISC-V we can have supercomputers, I mean high-end supercomputers in production before 2028, 2030. So we move slowly. It's not, when I say we, it's not just cyber, this is the industry. The industry is moving slowly toward RISC-V, but is moving to RISC-V. So we have anticipated with the European Processor Initiative, and we are combining on the same roadmap ARM and RISC-V. So this is what is described on this chart. The short term, we embed in the first generation of microprocessor that is described here, why not directly, some accelerator IP with a tensor accelerator, with a vector accelerator, with a stencil accelerator and an FPGA. And through time, through the generations, we will add more and more RISC-V compute IPs, including at some point of time, general purpose compute IPs. Yeah, and something very important as well, through time, we'll move to a single die. So what's inside what we call a socket. This is a package. Inside the package, today it's a single die, a single piece of silicon. So AMD did introduce a concept of multi-die, multi-chiplet. So all the industry is moving to this sort of assembly inside the package, because this is the only way to have a giant packages and giant processors. So we have designed the REA processor. REA is the code name and the commercial name of the first processor we are designing. REA is the mother of Zeus, because the core we are using, the Neoverse Z1, its code name at ARM is Zeus. That's the rationale behind. So obviously there is no number on this slide because it's still under NDA. So I will be very happy to disclose more, but contact me and we'll sign an NDA and I will disclose. So it is based on the ARM instruction set, Neoverse Z1. What is very interesting, I think that is very interesting for the developers and the end users, we use reasonably short vectors, 256-bit long vectors. So it means that in terms of application optimization, it's much easier to use 256 long bits than to use 5512 or 1024 bits long vector. If you have worked with a Knight series from Intel, it was a nightmare to optimize just because of the so long vectors. Even today, optimizing an application for AVX 512 is very complex. Most of the time, you cannot obtain the best of the peak performance just because of the long vector and the limited memory bandwidth that is associated with the long vectors. So you have a very poor, let's say, information flow per cycle toward the vector. So in terms of metric, this is the byte per flop ratio. How many bytes per floating point operation per cycle? So today, the metrics in the industry is about 0.1, meaning that just to get 1 byte, you need 10 cycles. It doesn't make sense. You have a fantastic core with long vectors that can work like hell with massive floating point operations, but you cannot feed it. So it's just something that doesn't make sense. So we try to solve this issue with shorter vectors and implementation of HBM on the die. So with massive memory bandwidth with HBM on reasonably limited vector length, meaning that we will really improve the byte per flop ratio, really improve, at least by a factor of 2 to 3 compared to Intel and AMD, and even compared to the best-in-class CPU, which is in a Fugaku machine, will be at least twice better. So we think that for most of the users, just using -03 optimization flag will be enough to obtain very good performances. Because the compiler has, I wouldn't say the compiler has nothing to do. It has very limited work to do. So the developer has very limited job to do to obtain performances. As a consequence, the developer can spend more time on GPU optimization. So the less time you spend on CPU, the more you spend on GPUs. So it's better for everybody. So this is the real objective of the machine, of the CPU we are designing. So combined with HBM, we also have DDR. In order you can have all the services, let's say file system, Linux, and all of that in the slow memory, because it's just stupid to use HBM for running Linux, and you can dedicate the HBM memory for running. And I'm going to elaborate on that in terms of co-design. Top of that, we'll have lots of PCI Express lanes and CXL connections with PCI Express. In order, we can start combining the memory from the CPU and the memory of the GPU together in the same model. So it's not yet CXL type 2 that will unify the memory between the CPU and the GPU, but at least we are implementing type 1 and type 3, which is the memory on one side or the memory on the second side. So that will be an intermediate step that makes a lot of sense toward the future. For us, it's important to work with a CXL because it is a standard. We don't want to enter a proprietary approach like NVLink, like Hyperlink, because we believe that you, as end users, you want to have the possibility to switch from one physical environment, one hardware, to another one with no effort to report, to re-optimize, to recompile, to re-debug, and so on and so forth. So we want to avoid that. This is why we prefer to be maybe one step behind in terms of integration of technology, but just to work with standard technologies. It's very important. And all the cryptographic and security features are 100% designed in Europe by European people. So if we have a specific request coming from a government in terms of audit, in terms of backdoor control, we are on the safe side. That is also very important. When I say that we combine CPU and ARM and RISC-V, you can see here what I am talking about. So I prefer to explain in the later slides what I mean with STX and ERAC. You will see some concrete examples. And this is something that could be of interest for you to test. Everything about RISC-V is either control cores, something you don't see for the clock control, for the power monitoring control, and power capping control. So it's totally invisible. What is visible is the acceleration IP, acceleration block that we implement in the processor just to test. It's a unit acceleration block just to test the application. There's no way it can be put in production at a large scale. It's not designed for this purpose. This is for testing. So the first acceleration IP we are implementing is developed by the Fraunhofer Institute as part of the European Processor Initiative. This is a stencil, so I don't know whether the bioinformatics and the applications you use to work with make massive use or not of stencil, but this is designed for the most classical let's say, HPC and mathematical and numerical models. So everything that is explicit in time makes massive use of stencils. So this is an area where co-design makes a lot of sense. There are very little changes to do in the source code. It's mostly Pragma to and then to recompile, obviously, to test this stencil. And from the very early comparisons with classical GPUs, and the one that has been compared is the Ampere A100 from NVIDIA, on the two oil and gas models, so it's not in your activity. It is for reverse time migration and reservoir simulation. In terms of mega stencil per second per watt, this is at least 3 to 9 times better than A100. So it's very, very promising. It's a very promising technology. So for stencil, it's very specialized, but it is designed for this purpose. And again, for this, HBM will make a big difference in terms of performance. Going to move fast. Something that is also very interesting with a strong potential is an IP for variable precision that is designed by CEA. And the goal is to minimize the effort in terms of precision. So instead of reducing the precision, you increase the precision dynamically on the fly in order, for instance, instead of using an inverse method or indirect method to solve a matrix, you can keep using direct methods. This is just perfect for the Hill conditioned matrices. So this is designed specifically for this need, and you can really reduce the time to result by a factor of 10 to 50, depending on the matrix and depending on the specifics of your model. You can also reduce a lot the effort on the preconditioning phase of preparing your matrix. So this is something with a strong potential, but it has to be understood and analyzed in detail for each mathematical model on each domain to better understand whether it makes sense to use it or not. That is also something interesting for co-design. Another point for co-design is how to make a good use of the memory. I did mention we have HBM and DDR. It's not a unified memory. It's not HBM as a cache. It's in Linux, you will have two different memory spaces. One DDR, one HBM. So we have to work together, and this is something my team is ready to do, to support you to take advantage of the two memory spaces. Maybe it's a bit more complex to use, but when it is done, when the job is done, it works. I'm very practical. I know that we already had this kind of technology in the past in the night landing series from Intel. But in the night landing, you also had the possibility in the BIOS to switch to HBM as a cache. All users said, oh, having separate memory is the best way to go. And all of them activated the HBM as a cache mode because it is much easier to use. So I know that this is not optimal for developers because they will have to spend some time to make the difference between the two memory spaces. And I know that for REA 2, that will contain HBM as a cache. They will forget this and move to HBM as a cache working mode. But anyway, I know that for the people making the effort to use it properly, that will be very, very efficient. So we will have a board that will be ready for testing, and this is designed with Atos. that will be ready for testing in say September next year, September, October next year. That will be a single socket or dual socket board with the different PCI Express and extension you can that you can see here. On the right hand side, you can see the very let's say simple representation. On the left hand side, you can see the detailed view on the different attachments you can have on the board. So it's quite flexible with a lot of different possibilities. Performances, something I used to show, and I will move very fast through this segment. So to make it short, when you want to maximize the flops, you go to GPUs. When you want to minimize to maximize the memory bandwidth, you go to CPUs. On the x-axis, this is the peak in gigaflops or teraflops. On the y-axis, this is the byte per flop ratio. So you can see that the CPUs are more and more on the y-axis with very low gigaflops or low peak performance compared to GPU. So making any kind of comparison between CPU and GPU on peak performance and lean pack peak performance is just stupid. This is a game that CPUs just can lose. And the byte per flop ratio is associated to the HPCG benchmark, which is a solver using an indirect method, a conjugate gradient for matrix. And when you look at the efficiency per watt, you can see that when you combine ARM instruction set and HBM, not only you have great performances for HPCG, plus you've got much better performance per watt. And for most of the applications not fitting in GPUs, the matrix of choice is HPCG. So if you want to have the right combination of CPU and GPU for performance and performance per watt, the best you can do is to make the right choice for the GPU from this standpoint, and for the CPU to combine ARM and HBM, and you will have the most optimal approach. So here, this is mostly for you to read offline, just to say that one of the big advantage of ARM instruction set, it's a modern instruction set. So for the most usual operations, addition, multiplication, division, FMA, square, blah, 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 the number of cycles to perform the operation is reduced with ARM compared to x86. So it is one of the reasons why ARM is better than x86 in terms of performance per watt. Because for doing the same, you need less cycles. This is public information now. So you have the reference at the bottom of the slide. So you can see it represented differently, but all of that is really for your understanding. In terms of HPCG efficiency, so we think that with the REA processor, the green bar will be around more than 7% and close to 8% of the peak is the peak performance. So the ratio between HPCG and peak will be 8%, around 8% on REA, compared to what you can see with Genoa, A64FX, and Sapphire Rapi. So we are much more efficient on this standpoint. So on here, you can see the flops per gigahertz, which is also an important metric because gigahertz is also associated to performance and to power consumption. So from this standpoint, you can see on the A64FX and Sapphire Rapi the benefit of HBM, but they use long vectors, 512. While you can see an additional step of benefit with REA because of the SV256 vector length. So more or less the same. And that's it. I've been very short. I could spend hours on the performances, but I wanted just to show you that with REA, We don't focus on peak performance, definitively not. We focus on real efficiency for the real applications. And my key strategic focus is to deliver to the end users a processor that is very easy to use. You compile and boom, it works. This is all what I want. I want you to spend your time on GPUs and you don't waste 1 second on the CPU. This is my objective. That's it.
Thanks, Jean-Marc. So again, you've got a remote audience as well. Can we just see if there's anyone out there who would like to pose a question for Jean-Marc? Any hands up? I don't see any, do you? No. And what about someone in this room? Ivan at the back. Speak up.
I'm interested in which compilers you need the ARM compilers.
So that's a very interesting question. So obviously we've got all the open source compilers because ARM is familiar to push to the GCC on an LVM their instruction set. So the job is already done. We have an agreement with Intel to have the REA processor fully supported in the Intel compiler well, very soon. We have closed an agreement with NVIDIA as well, with HPE, so we'll be supported in the Cray compiler, and we are still discussing with AMD, and we see in the future if we can be supported in their environment. So my objective is to be supported in all compilers.
Any other questions? And Samuel and you, Jean-Marc, are involved with the Jupiter machine, and we heard a bit about that earlier from Gerd Matthias from LRZ. Do you have any comments to make on that? How it's going to evolve, what it might look
You are
like?
moving too fast to say that we are associated to the Jupiter machine. So Jupiter will be the name of the German exascale machine. I did mention that the objective of EuroHPC is to have the European processor in the European exascale machine. So the shortcut is we are going to be in Jupiter, which is right as long as we are on time, we deliver a product with the right features, with the right performances, I mean, comparable to the best in class from Intel, from AMD, or maybe from NVIDIA, and at a price that is also compatible with the competition. So to tell that differently, EuroHPC will not use the European processor, whatever it takes. They will use it if we can make the job.
Okay.
That's a strong restriction. It is a real competition.
Any other thoughts, comments? Ivan, you wanted to?
Another question about the stencil accelerator they're going to be on Dragman. So I'm aware of other stencil accelerators. One is YAS, and I know Nick. So I wasn't able to see whether these Dragmans are that they existing.
No, it's new ones.
So they are.
Yeah. Now we can talk about it in detail, and I will involve Fraunhofer Institute in the discussion because it's coming from them.
I don't see any other questions now. We've overrun a little bit. Oh, there is one.
Maybe one question. Well, it will be more a practical question. So if we want to engage with you, we as a environment, and what can we expect in terms of collaboration?
So we are not experts in your domain. So meaning that you know your applications, you know what you are doing, you know your algorithms. So what we can do is to support you, to help you. So as I did mention, Atos is designing boards and servers based on REA. So when the servers will be ready, So it's very likely that Atos has a number of Combiomed, and through the Center of Excellence that Natalia Jimenez is creating, that you get access to this kind of equipment. So with the help of the Atos people like you, and my benchmarker and compiler experts and engineering experts, we help you to obtain the best, to get the best out of the CPU, to train you on the usage of the right compiler flags, how to change this loop on that loop the right way to optimize, how to make the split, to make the best usage of the memory, and so on and so forth. So we are just coming with a strong expertise on our CPU and how to use it, and that's it. We just want to transfer our expertise to you.
So it's good that you mentioned Natalia Jimenez from Atos. I'm not sure how many people here are aware of her, but I mentioned that I'm involved in the launch of that Center of Excellence.
Yeah,
They have their own Life Science Center of Excellence that's going to be launched. It was originally 2 years ago, but COVID delayed it. It's being launched for me on the 30th of June. It's on the Wellcome Human Genome Campus in Cambridge. So that's part of Atos, and it's good to hear you pointing out their connection, because they are part of what our opportunity.
Yeah, and I see that Natalia is connected.
Yeah. Okay.
She's also presenting tomorrow.
She's going to be talking as well, so probably about the center of it. Good. I think that's it then. John Up, thank you very much indeed. You can
My
now
pleasure.
head off to the airport, so we will remain
No, that's
in
okay.
contact.
I've
We
been
have
too
the-
long, sorry.
No, don't worry. It was important for people to know this. There's now a question. Is there one?
It's a clapping hand. Oh, I see.
Nothing else. They liked it.
It's a
Good.
sum up.
So-
That's it.
So we have a coffee break now. And if you can mingle a bit with people to answer questions, that would be great. And then you can head off and we restart with Narges, I think, correct?
We've only got
So-
10 minutes now. so-
Yes, 10 minutes.
Okay.
Yeah.
On anyway,
Because
there
it
is my
starts-
email, and I will send you the PDF of the presentation.
Yes,
So
please do.
you can distribute.
That would be helpful.
And if you have any question, you contact me, and I will be so pleased to put you through the right people in my team and to answer any of your questions. And
Great.
anyway, you are very lucky because Atos is part of Combiomed,
Yes,
and Atos is part of EPI. Atos is very, very committed to REA, so Atos knows a lot about what we are doing. So you can use Atos.
okay, thank you very much. Should we come back at 20 past? So you only got
Yeah.
10 minutes. Sorry, I looked up. You need to make sure you're ready to speak. Thank you very much.
But I guess I can now log out from the chat.
Yes.
Just to display it.
Oh, yeah, do you want to put share screen on
Need to show
with this one?
Yeah. Oh yeah. Oh no, that one. No, 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 no. This one.
Ah, yeah, okay, yeah, 'cause you want-
This one I want.
Are we all set? You're
Yes.
you're happy?
Yes.
Okay, welcome back after that coffee break. We now have a session of a range of sort of applications, but the first one off is from Narges Zarrabi, who is at SERP and will be speaking about something that is unpronounceable except EOSC is, and that stands for the European Open Science Cloud. You're going to talk to us about federating sync and share services.
Good afternoon. I'm Narges Zarrabi. I'm advisor of data services, research data management at SERP. And it was, I think, 2 months ago that a colleague of mine who is involved in a European project called CS3 Mesh for EOSC approached Marco and I and asked if Compiomed can make use of the services that they are developing in their project. And the first question is asked, what is it that you can offer to Compiomed? And that was for me a learning phase to getting to know this project and see what type of services they have. And the idea of my talk today is to, well, introduce it to you. Hopefully you can find it relevant to the research you do and say, I am doing this type of research. I need a cloud storage that I can share data and so on. So I hope that I can introduce the project to you well and that you can relate it to your work and hopefully come up with cool use cases. Before I go into the slide, I'd like to show you a 3-minute video. Well, this is my colleague, Ron Trompert, who is actually involved in the CS3 Mesh for EOSC project. So this is going to save me later some slides with text. So I would say just see these 3 minutes of video and then I'll talk more. Can collaborate with colleagues anywhere in the world using these services. So the keywords here has been federation, collaborative working, and especially in international setups that a lot of partners are involved. These services will be useful. So what is a sync and share service? It is a service or a storage on the cloud that you put your data. You can easily share your data with others and collaborate with them at the same time. You can make your data synchronize over multiple devices. I have some icons. And there are some built-in applications for data analytics, editing documents, like you will see in the next slide. So it offers a lot of things like sharing files and folders, collaborative editing, also roles and permissions that someone has control over the data and can give permissions about for data to be accessed by others. International access is possible, so not only people who are involved in your project or in your institute can get access to the data, but you can give access internationally. And well, large storage amounts are possible to get. You will also, they are also called so-called enterprise files synchronization and sharing. So this EFSS refers to the same sync and share services that we talk about. You will see it in the rest of the slides. Examples of such services are here. I'm sure you relate to some of these icons: Google Drive, Dropbox, are services that you might have used to upload your data in cloud, share it with others. But these services are not always advised to use, especially if you are working with research data. You want to make sure your data remains in Europe, doesn't end up in whatever server in the US or so. There are a lot of these sync and share services being developed by institutes or organizations. And what is CS3 Mesh for EOSC about is actually a project that brings all these sync and share services together. I find it in the first very complex name, so I have divided it into parts. So the CS3 is actually the community around these sync and share services, which I'll introduce later. The mesh is referring to a science mesh, basically a federation of these services, which enable you to collaboratively work on documents, on data analytics, and a so-called federated data cloud, science cloud. And then all these in the context of the European Open Science Cloud. So I hope the name doesn't, scare you. It's a complex name. But in the remaining of the slides, I will explain more what is what. So the CS3 community is, as I said, the community around these sync and share services. There are more than 70 institutes involved worldwide that have their own sync and share service in 25 countries and more than 147 participants in this community. It refers to the cloud storage service for synchronization and sharing. And as you see, it's a big community. So at some point, these individual organizations that have been developing these services come together and form this CS3 community. It was a really bottom-up approach. So they basically formed the community somewhere in 2014 and tried to federate or connect to each other by the services that they are, the EFSS or the enterprise file sync and share services that they develop. So you can see that research labs, universities, companies, they might each run their own instance of such a service, and it's relatively easy to federate those. Again, some numbers, more than 400,000 users are using these services within this community. 16 petabytes of data, billions of objects are stored in these services. And the aim is to facilitate research and offer data services like big data science, supporting education through this cloud-based environment that are getting federated and offer interesting applications, as you will see. There has been also conferences every year in this community showing the updates and progress within that. So they moved up the stack by really integrating interesting services for collaborative working or research interfaces for data analytics, like Jupyter notebooks, for education, for trainings. They have integrated with data repositories, like you have your data somewhere in the cloud, imagine Dropbox, but other sync and share services, and then ways to add metadata to this data and push it to a data repository to get published. So these are the type of developments that has been done over time, and also trying to support open data and publishing data. So from being pure cloud storage systems or service, they are now developing, the community is developing itself to support fair data, science, big data analytics, and so on. So yeah, as you see, from simple storage facilities moving to really supporting data science and research environment. And so the project CS3 Mesh for EOSC comes into picture. It is a Horizon 2020 project, started in 2022 until I think it should be starting in 2020 until 2023. This number is 2022 is by mistake. And the idea is to, as I said, federate all these individual sync and share services that are developed among these community, to make them federated, to make them operate in a way that collaboration can be done among different research institutes. It supports open source software. It's built based on open source software. And is trying to also promote fair and open data. And it's built in a way that is decentralized and also sustainable, because most of these service providers involved in this community are like those who are running the service in production. And there is only this little cost of coordinating, well, not little, but bringing them together that is supported by these EU project. So there are a lot of plans about the sustainability of the whole thing, and they are trying to set up this so-called science mesh, which is again a federation of these sync and share services through this whole European project. And what is science mesh? It's a decentralized mesh of these sync and share services. It's based on open standards and open source software, which you will see later. It's a federated environment where researchers can easily collaborate, and also provides application platforms like Jupyter Hub or Jupyter Labs, or OnlyOffice for editing documents. So the use cases that are currently running are in different fields that facilitate collaborative data science in astronomy fields, finance, IoT, Earth observations, high energy physics, smart cities, but also pharma, and eventually in every business that is out there. There is need for uploading data somewhere central, being able to collaborate, share, and this is the core business of these services. LOFAR is one of the communities that is using the services of CS3 Mesh. They gather a lot of data, astronomy data, you know that it can grow a lot. And then they need to do this data transfer between these different sites. For example, there is LOFAR data being stored at SURF, and it needs to be transferred into some other center, into Krakow, for creating science quality images. And there are tools like rClone, for example, which is very similar to rsync, but for cloud services, that facilitates this data transfer. And there are development being done using these technologies listed here to make it even more performant and on demand. So data transfer between research groups is one of the things that they are hardly working on, and putting a lot of effort to facilitate data transfer between these federated sites. The other use case is about the Earth observation, and a project so-called MISLAND, which they study the degradation of the land with data analytics using Jupyter. So this Jupyter is actually an application that is integrated into this sync and share service. So imagine that you log in into some cloud environment, and then there is a button that redirects you to the Jupyter Hub. And then you have access to your data in the cloud, and you can run this application in the cloud and then analyze your data. So it is a very powerful tool for data analytics, maybe not very heavy, but depending again on the compute power behind it. But it's a very strong tool for doing, let's say, lightweight data analytics and also education. Yes. The other thing they are working on is fair data, as I mentioned. So you can see that here in the left, you have the sync and share platforms like OnCloud is one of the providers of sync and share service. It's open source, the enterprise, the community version. And at University of Münster in Germany and some other collaborators are developing a middleware that facilitates adding metadata to this data and then pushing that to any repository out there, like Zenodo or DataCite, or based on plugins. So if you publish your data in Figshare or it can be integrated via, by developing a plugin and then integrated into this system. So again, imagine you have your data somewhere in cloud, you have analyzed it with Jupyter, you have some output data that you want to annotate with metadata and publish it in Zenodo or in Fixture. With this RDS tool that is being now developed, and I think in a beta phase, this workflow can be done. At Surf, we are also hosting 2 single share services, the Surf Drive, which is more cloud-based storage for personal documents, but also Research Drive, which is more oriented toward research data. And we have developed a lot on top of the OnCloud, which is the underlying single share technology meant for research data management. So you can imagine that a university has a lot of users. They want to give them cloud storage. They want to share data. So there are different roles defined in this tool, in this service called Research Drive, and the normal users can just log into the cloud, upload data based on the rights they have, use the integrated applications like the Jupyter Hub or OnlyOffice to collaboratively edit or analyze data. But there are also power users, like those in charge of the IT. They can have a good overview of which data is shared with whom, or an overview of the projects in the system, and also having, admin rights in the system. And it's all connected to the storage in the backend, which is currently Object Store, but we are looking into ways to replace it with a better performing storage system like Scality or other storage types. So, not very much about compute, but I believe that any compute needs data to be stored somewhere that is easily accessible and can be shared and collaboratively work on. So these are the type of services that can be of use. For the Research Drive service, you can request access through the EOS portal via the B2Drop. So B2Drop is the European version of it, where we offer the similar single share service called Research Drive at Surf, and it can be requested via the EOS portal. So if you think you are doing a research that you would require to share your data with others, give access, have control over your data, you can request for this via the EOS portal, and the cost will be reimbursed through the DICE virtual access. So I hope, this brings me to the end of my presentation. I hope you've got an idea of what these services are about. If you want to talk later or ask questions, feel free to do.
Narges, thanks very much.